So hi guys, we are back with another video that is going to discuss the calorimetry part in the thermal physics, right? So yes, let's get started with. Before we get started with, I would like to say we initially will be solving some normal questions, right? So like not very complex questions in order for you to absorb the theory content. I'll be doing some normal questions, and then thereafter let's go for some difficult questions. All right. So yeah, these things are pretty basic. I guess you can figure them out. So let us go for the fourth question. Let's discuss from the fourth question onwards. So it says a lead bullet with constant velocity of 26 meters. Okay, a lead bullet with constant velocity 26 meters comes to rest. Okay, comes to rest after hitting a target. If the whole if whole of the kinetic energy of the bullet is converted into heat, they're saying if the complete kinetic energy of the bullet is converted into heat, find the raise of the temperature of the bullet. How much the temperature of the bullet is raised. That is what they are. Right. So let us see the question. Right. Okay. So this is the fourth question. Right. So it's like this. So there's initially a bullet. Right. So and yeah, it's like this. Right. Then they're saying a lead bullet moving with constant velocity 26 comes to rest. Okay, so this was initially moving with u equals 26 meters per second. After it strikes this, it will come to rest. It will come to rest, right? So and then also they're saying if the whole lot of kinetic energy of the bullet is completely converted into heat, they're saying that, right? So you'll have to assume that the complete kinetic energy, all the kinetic energy that it had, is converted into heat. So what has happened actually? Kinetic energy lost has been equal to heat energy gained, right? Heat energy gained. So what is the kinetic energy loss? So initially it had a kinetic energy half m u squared minus half m v squared. This is the kinetic energy that was lost. Heat energy gained is written how? M, specific heat capacity, and delta theta, how much the temperature of the bullet increased, right? So actually this is zero, like, because finally it's going to come to rest, right? So therefore the final kinetic energy is zero. So initial kinetic energy is now half m u squared is equal to m c delta t. So theta. So this to this cancels, m to m, right? So what we need to find is the increase in temperature. So increase in temperature can be found u squared over 2c. So if we apply the values 26, so they're saying 26 squared divide by 2 into what is the specific heat capacity. They have given the specific heat capacity to be as 130 joules, 130 joules per kilogram per Kelvin. Somehow, if you simplify, you are going to get this to be as 2.6 degrees Celsius. 2.6 degrees Celsius. Actually, what has happened is the total kinetic energy lost, right, has been used to increase the temperature of this bullet, right? So kinetic energy lost is equal to the heat energy gained, right? Okay, fine. So let us discuss the fifth question as well. In the fifth question, what they're saying is a heater of power 100 watts. So there is a heater of power 100 watts. It takes 5 minutes to heat. They're saying it takes 5 minutes to heat a metal block. 5 minutes to heat a metal block of mass 2.5 kilogram by 24 degrees Celsius. Find the specific heat capacity of the metal. They're asking us to find the specific heat capacity of the metal. And then also they have said us neglect the heat loss to the surrounding, right? So what they're saying is a heater of power 100 watt take 5 minutes to heat a metal block of mass 2.5 by 24 degrees, right? So let us draw a figure for that as well, right? So if we see, so there is maybe a metal block, right? So this metal block is heated using a heater. So this works with a power of 100 watts. 100 watts. For how long? For 5 minutes. 5 minutes, right? So what is the mass of the metal block? What's the mass of the metal block? Mass of the metal block is 2.5 kilograms. Mass is 2.5 kilograms, right? What's the like when you heat it, by how much did the temperature of the metal block increase by? It increased by 24 degrees Celsius. 24 degrees Celsius. So what has happened here? Who is supplying the who is going to supply the power? Sorry, the heat, and who is going to absorb the heat? Actually, the heater is going to supply the heat. Heater is going to supply the heat. The heat supplied by the heater is going to be absorbed by the metal block, right? And then because like they're saying no heat loss, right? There is no heat loss to the environment, no heat loss, right? So therefore we do not have to consider those things, right? So here heat supplied, simply we can deal with this as heat supplied by heater equals to heat absorbed by metal block, right? So how do we write the heat supplied by the heater? Actually, how is the heater supplying heat? By like electrical energy. Electrical energy is converted into heat energy, right? Electrical energy is converted into heat energy. So power can be written as how? E over T, right? Power of a heater can be written as power is equal to electrical energy E over T. So therefore the electrical energy can be written as P into T. So therefore the heat supplied by the heater can be written as how? P into T. Heat absorbed by the metal block, how can you write? MC delta theta, right? They have given the power 100 watts. Time they have given 5 minutes. But usually when we substitute it in SI units, we have to convert it into seconds. 5 into 60. What is the mass? Mass was 2.5, I guess, right? 2.5, yes. 2.5 kilograms. C is unknown. The increase in temperature was 24 degrees Celsius, right? So if you simplify this, you're going to get the answer 500 joules per kilogram per degree Celsius, right? So this is simply how you solve this question. All right. Right. So let us go for the sixth question, right? So in the sixth question, what it says is a beaker contains 100 gram of water, right? A beaker contains 100 gram of water at 60 degrees Celsius, right? So a beaker has 100 gram of water in 60 degrees Celsius. Let us initially try the problem by drawing, right? So this is the seventh one. Is that the case? No, sixth one, right? So yes. So initially there is a beaker, right? There is a beaker which has water which is in theta 1 is in 60 degrees Celsius. How much is there? 100 gram of water, right? Mass was 100 grams, right? Then they're saying the temperature of the water is to be measured by the mercury thermometer. The temperature of the water is to be measured by a mercury thermometer. Find the temperature registered by the thermometer if the heat capacity of the thermometer is find the temperature registered by the thermometer if the heat capacity of the thermometer is 84 joules, right? Okay, they are inserting a thermometer, right? They're inserting a thermometer, right? Now the C value, the specific heat capacity of the thermometer is 84 joules per Kelvin, right? Joules per Kelvin. And then they're saying the thermometer is initially at the room temperature 30 degrees Celsius, right? Thermometer is initially at room temperature 30 degrees Celsius, 30 degrees Celsius. All right. Okay. And also they have given the specific heat capacity of water. Specific heat capacity of water is given. So specific heat capacity of water is given 4,200 joules per Kelvin per kilogram, right? Okay, fine. Now, actually, how does a mercury thermometer show a certain temperature? Actually, what do you think? What happens is the water column is in higher temperature. Initially, the water column is in 60 degrees temperature. So what happens is there's a temperature difference, right? This is the water column is in 60, the thermometer is in 30. So definitely from the water column to the mercury column, from the water column to the mercury column, heat is transferred, right? So who is supplying the heat? Water, right? So it's written as heat supplied by water. Who is going to absorb the heat? The mercury column. Heat supplied by water, heat absorbed by mercury column, right? Heat supplied by mercury column, right? Heat supplied by water is equal to heat absorbed by mercury column. So, right, actually, now you need to understand, after heat is being supplied by the water column to the mercury column, so this is going to rise, right? The mercury column is going to expand, and it is going to come to a constant temperature. Actually, it's going to come to a uniform temperature, theta 2. After absorbing heat from the water column, it's going to reach to a equilibrium temperature. Let's assume that is theta 2, right? So in that case, now you need to understand, not like when the mercury column reaches an equilibrium temperature, like if it is in thermal equilibrium, both the mercury column and the water column should be in the same temperature, right? Like after a while, what happens is both the thermometer and the water column shows theta 2 temperature, like because it's in thermal equilibrium, right? So it's in thermal equilibrium, right? So fine. Now it's like this, right? So let us assume the initial temperature of the water column is theta 1 dash. Heat supplied by water. Finally, water reached what temperature? The equilibrium temperature, theta 2, right? So heat supplied by water can be written as how? Heat supplied by water. We can write the heat supplied by water is MW CW. What is the increase in temperature? Sorry, what is the temperature difference? Initially, it was in 60 degrees. After it supplies heat, its temperature should decrease, right? You know that. After water column transfers heat to the mercury column, the temperature of the water column should decrease. So therefore, it should be theta 1 dash minus theta 2. Theta 1 dash minus theta 2. This should be equal to the heat absorbed by the mercury column. So heat absorbed by the mercury column, right? So actually, they have given the heat capacity, not the specific heat capacity. Remember, they have given the heat capacity of the mercury column. So therefore, when we write the heat absorbed by the mercury column, we need to write C theta. You know, right? So when you deal with heat Q, you have two equations, mc theta. Also, you can write Q as C theta, right? So in this case, mass and the specific heat capacity should be there. If you are dealing with, if they have given you the heat capacity, only the heat capacity and the temperature difference is more than enough to get an idea about the heat absorbed or heat released, right? So if you are going with the specific heat capacity, definitely you need the mass as well, because of the definition of this heat capacity and specific heat capacity. We have discussed about these things, right? So therefore, I guess you are pretty clear on that fact, right? So now these answers, these values, I guess everything is given. Mass of water column is 100 grams, right? I will write it in kilograms. So this is 4,200, and theta 1 dash is what? 60 degrees minus theta 2, C is what? 84. Theta is what? 84. Okay, sorry, MC. When you write the heat absorbed by mercury column, you need to write the temperature change as well. So initially, the mercury column was in what temperature? 30 degrees. Actually, the mercury column is going to absorb heat. The mercury column is going to absorb heat. When the mercury column absorbs heat, its temperature rises, right? Its temperature rises to what? The equilibrium temperature theta 2. It's going to rise to equilibrium temperature theta 2. So therefore, it's theta 2 minus theta 1. What is theta 2? That is what we need to find. What is theta 1? 30 degrees Celsius. So if you simplify this, you're going to get theta 2 to be as something around 55 degree Celsius. You're going to get 55 degree Celsius, right? This is a good question. You need to understand it pretty well, right? Right. So let us discuss the 7th question, right? So here it says the temperature of the water of a waterfall is 20 degrees Celsius, right? The temperature of water of a waterfall is 20 degrees Celsius at the top, and 20.3 degrees Celsius at the bottom. 20.3 degrees Celsius at the bottom. They're saying considering all the kinetic energy of water converts into heat, find the height of the waterfall. Right. So let us draw a figure for this also. So simply, this is the 7th question, right? So there is a waterfall, right? So let us assume this is a waterfall, right? So the temperature, like let's assume m amount of water column is going to fall. At this moment, the temperature of the m amount is 20 degrees Celsius. They're saying the water column on the top of the waterfall is 20 degrees Celsius. When it falls on the to the water surface, right? So when it falls to the water surface, they're saying the temperature at the bottom was supposed to be 20.3 degrees Celsius. 20.3 degrees Celsius, right? They're asking to find us the height of this waterfall. They're asking us to find the height of this waterfall, right? So then they are also saying consider all the kinetic energy. Consider all the kinetic energy of water converts into heat. So actually, how is the energy converted? Initially, if you consider this as the potential energy 0 level, right? Initially, it has a mgh, right? So actually, the potential energy converts to what? Kinetic energy. So initially, the water column doesn't have any speed, right? Let's assume it's 0, right? Initially, it doesn't have any speed. Like all these potential energy, like initially, it's at a certain height, right? All this potential energy converts into what? Kinetic energy. All this potential energy is converted into kinetic energy when the water column reaches somewhere here, right? When the water column reaches somewhere here, it's going to reach with a certain velocity, kinetic energy. And then they are saying next they're saying us to assume that all this kinetic energy converts into what? All this kinetic energy converts into heat energy. All this kinetic energy converts into heat energy. So yes, we can omit the middleman here. We can omit this middleman here, right? And we can say the potential energy loss. So if we consider this water column of mass m, right? Potential energy lost is equal to heat energy gained, right? Heat energy gained. So potential energy lost is what? mgh minus the potential energy at this point is what? 0. The potential energy at this point is mgh. The potential energy at this point is 0. So potential energy lost is mgh minus 0. So what is the heat energy gained? So the same water column is going to absorb all the heat that is generated. That is the assumption. That is how the temperature increases, right? So you can see initially the water column had 20 degrees Celsius, but after it fell, its temperature has risen. That means it has absorbed heat. From where does this heat generate? From this potential energy loss. So the potential energy loss is equal to the heat energy gained, right? M C delta T, mc delta T, right? So if you see mgh is equal to mc delta T, m2 m cancels. So what they are asking us to find is the height of this thing, right? So h is equal to c delta T over g. C is given, right? C is given to be as 4,200 joules per Kelvin, and the temperature rise is what? 0.3 degrees Celsius, right? 20.3 minus 20 degrees Celsius. This is the temperature rise. The temperature rises by 0.3 degrees Celsius. So therefore, delta T I substitute it as 0.3 and divide by 10. So the height you're going to get as 126 meters or something, right? So I guess that question is also understood, right? So let's discuss the 8th one as well, right? So here it says a current of 2 amperes. A current of 2 amperes is passed under voltage 10 volts for 10 minutes through a heater. Immersed in a liquid in a copper calorimeter, right? So let us draw that initially, right? So they're saying they have a copper calorimeter, and this calorimeter is heated by using a heater, right? A heater. So let us assume inside the copper calorimeter there is some liquid, right? So they are sending the current for how long? So they're sending a current I is equal to how much? 2 amperes. They are sending a 2 ampere current of voltage 10 volts, right? Of voltage 10 volts for how long? For 10 minutes. Right. They're sending this, right? Let us read the next. Mass of the calorimeter is 0.25 kg. Mass of the calorimeter is 0.25 kilograms, right? What else? And the mass of the liquid is 0.1 kilograms. Mass of the liquid is 0.1 kilograms, right? If the rise of the temperature of the system is, so when actually by a heater, what does it do? It supplies heat. So when it supplies heat, let us assume the temperature that was risen, or is the rising temperature was 20 degrees Celsius, right? Both the calorimeter and the liquid rised by 20 degrees Celsius. They're saying the specific heat capacity of the liquid, find the specific heat capacity of the liquid. If that of copper is, they have given the specific heat capacity of the copper. They have given the specific heat capacity of the copper to be as what? 400 joules. 400 joules per kilogram per Kelvin, right? So yes, they have given this, right? Okay, fine. Now, what they are asking is the specific heat capacity of the liquid, right? So you need to basically understand how the heat transfer occurs here. Actually, when electricity passes through this electric coil, right, heater, this coil gets heated up. So that heat energy is going to be supplied to the liquid and the calorimeter. So the liquid and the calorimeter, what does it do is it's going to absorb that supplied heat energy, right? So simply heat supplied by heater, is equal to heat absorbed by calorimeter plus liquid, right? Both of these guys are going to absorb the heat, calorimeter and the liquid, right? So heat is supplied by the heater how? As electrical energy. How do you write that? VIT, electrical energy, can be written as VIT. Therefore, heat supplied by heater can be written as VIT. Heat absorbed by the calorimeter, MC delta T, right? Heat mass of the calorimeter, mass of specific heat capacity of the calorimeter, and the change in the temperature plus heat absorbed by the liquid. How do you write? mass of the liquid, calorimeters, like the specific heat capacity of the liquid, and the increase in temperature. What is the voltage? 10 volts. What is the ampere? 2. What is the time? Time is it was supplied. This was supplied for 10 minutes long, which means 10 into 60. Right? We have to write it in seconds. Mass of the calorimeter is what? Mass of the calorimeter is 0.25. And what is the specific heat capacity of the calorimeter? Specific heat capacity of the calorimeter is 400. Right? 400. By how much did the system's temperature rise? 20. What is the mass of the liquid? 0.1. Cl is what you need to find. It was increased by 20 degrees Celsius. If you simplify, you're going to get Cl to be as what? This given answer, 5000 joules. 5000 joules per kilogram per Kelvin. Per kilogram per Kelvin. Right? Okay, fine. I hope that was clear. Okay, so let us go for the 9th question as well, right? So it says an aluminium kettle, right? So there's an aluminium kettle of mass 0.5 kg, contains 2 kilogram of water, which is at 20 degrees Celsius, right? So there is an aluminium kettle, right? An aluminium kettle, let's draw it, right? There is an aluminium kettle of mass 0.5 kilograms, 0.5 kilograms. This is the mass of aluminium kettle, right? Mass of aluminium kettle is 0.5 kilograms, right? And then they're saying contains 2 kilograms of water. It contains 2 kilograms of water. All right. It contains 2 kilograms of water. Fine. A heater, a 2 kilowatt heater is used to supply heat. A 2 kilowatt heater is used to supply heat. Right. A 2 kilowatt heater. A heater with 2 kilowatt power is used to supply heat. What do they ask? Find the temperature of water after 4 minutes. Find the temperature of the water after 4 minutes. Right. After 4 minutes. After 4 minutes. After 4 minutes, the temperature we need to find. Right. Okay. Initially, what was the temperature? Initially 20 degrees Celsius. Right. Initially, they were at 20 degrees Celsius. Right. Initially contains at 20 degrees Celsius. Right. This was at 20 degrees Celsius. Since T1 is at 20 degrees Celsius. Right. Now, what are we going to do? Right. Now, 20 degrees Celsius means both are in 20 degrees Celsius. Right. You need to understand. So water is also in 20 degrees Celsius, and aluminium, the aluminium kettle is also in 20 degrees Celsius. Right. Only water can't be at 20 degrees Celsius. Right. So you can understand that because both are in contact, thermal contact, which means both should be in the same temperature. Right. So now, simply heat supplied by kettle should be equal to what? Heat absorbed, right? Heat absorbed by water plus aluminium kettle. Heat supplied by water. For how long was heat supplied? 2 kilowatts means 2 into 10 to the power 3. 4 minutes means, actually this should be written as P into T, right? P into T. M, mass of water is MW. Heat absorbed by water written how? MW CW delta T. Heat absorbed by aluminium is MAL CAL into delta T, right? So what is the power of the kettle? P into 10 to the power 3, which means 2 kilowatts. What's the temperature? Sorry, the time? 4 minutes. 4 minutes means 4 into 60 seconds. Mass of water. What is the mass of water? 2 kilograms, right? The mass of water is going to be as 2 kilograms. So what is the specific heat capacity of Water, it's 4,200, right? Specific heat capacity of water is 4,200. So what is the temperature change? Let us assume. So when the heater supplies heat, after a while, the temperature of the water is going to be in theta 2, right? So it's going to reach theta 2. So the temperature change is theta 2 minus what? Initial temperature was 20 degrees Celsius plus mass of aluminium was what? 0.5. Mass of aluminium was 0.5. The specific heat capacity of aluminium was 900. They have given it. So even the this thing, aluminium, is going to reach to T2. Initially it was at 20 degrees Celsius. If you simplify, you're going to get T2 to be as something around 87.8 degrees Celsius, right? 87.8 degree Celsius, right? So let us go for the second part, right? The second part, find the time taken to boil water. We're asking the time taken to boil water. So boil means the water should boil at what temperature? Water usually boils at 100 degrees Celsius, right? Water boils at 100 degrees Celsius. So in order for water to boil at 100 degrees Celsius, what is the time taken? What is the time taken, right? The same thing we have to rewrite. P is known, T is unknown, delta T is known. Why? Because the final temperature of water should be 100 degrees Celsius. Initially it was at 20, so the delta T is 80, right? Delta T is what? Water, when water boils, it should be 100 degrees Celsius. So initially it was at 20 degrees Celsius. So delta T is going to be given to be as what? 80 degree Celsius, right? So the same equation we are going to rewrite once again, but only the time is not known. Like the time taken by the heater to heat this water column to 100 degrees Celsius. The time taken by the heater to heat the water column to 100 degrees Celsius. What is the power? 2 into 10 to the power 3. Time is unknown. Heat supplied by water, sorry, heat absorbed by water is simply the same old this thing, right? 2 into 4,200. Mass of this is 2, 4,200. Delta T is what? 80 plus heat absorbed by the aluminium kettle is what? The mass of that is 0.5. 0.5. The specific heat capacity of aluminium is 900. Its temperature increased by 80 degrees, right? So therefore, if you simplify, you're going to get the time to be as something 5.9 minutes, right? In minutes, you're going to get it to be as 5.9. So initially, you're going to get it in seconds. So you can convert it into minutes and see it's going to be 5.9, right? I guess that is understood.